Following on from my previous video, I've got another example question for parametric differentiation, which I'd like to cover before moving on to some parametric integration. So here we've got question 3 for questions 1 and 2 to check out my previous video. It says a curve C is defined parametrically by the equations x equals t into t squared minus 4 and y equals t squared minus 1, and we're told t is between minus 2 and 2. We're also told that L1 is the normal to C at the point 3, 0, and we're told to find the coordinate where this normal intersects the curve again. Okay, so I know you wouldn't have access necessarily to graphing software in the examination unless you've got a GDC, but we're going to have a look at this graph. So this is what it looks like. Okay, it's from t is minus 2 to 2, that's the whole thing. And the point in question is the point 3, 0, so that's down here. There it is. And we want the normal to that curve at that point, so that looks something like that. Okay, don't forget the normal is perpendicular to the tangent at that point, so it goes that way. And we're looking for where this normal intersects the curve again. So we're looking for this point here. There it is, C2. And we can see clearly that C2 has an x-coordinate somewhere between minus 2 and minus 1, and a y-coordinate somewhere between 2 and 3. So that's the kind of answer we're expecting when we get to the end of this question. But to break it down, we need to reverse all this. We first of all need to find the t value at this point, because we're not told that. Then with that, we can find the equation of the normal, and then with that, we can find the intersect. Okay, so that's the kind of path we're going to take. Okay, so first things first, let's find the value of t at this point in question. So we know that at this point, x is 3 and y is 0, which means t cubed minus 4t must equal 3, and t squared minus 1 must equal 0. Okay, both of these have to be true at the point 3, 0. So this was easier to solve. This is a cubic with a constant, whereas this is just a quadratic with no linear terms. So the solutions to this are t is minus 1 and 1, plus or minus 1, and check both of those. If I plug in t is 1 into here, I'm going to get 1 minus 4, which is negative 3, so that's not right. And if I plug in minus 1 into here, I'm going to get minus 1 plus 4, which is 3. So we know that t is equal to minus 1. But the important thing to note there is the value of t has to satisfy both the x and the y equations. Okay, it can't just satisfy one of them, it's got to satisfy both. So t is minus 1 is the value of t that I'll be using. Okay, now we can differentiate this to find dy by dx. So dy by dx, that's going to be y dot divided by x dot, where this is a differential with respect to t. And that's just by the chain rule. So y dot, that's going to be 2y on the top. Okay, the minus 1 disappears. And then the bottom, we've got a t cubed, so that's going to go to 3t squared. And then we've got a minus 4t, so that's going to go to minus 4. Okay, and we want to find dy by dx when t is minus 1. Okay, so that's at the point 3, 0. So if I plug in minus 1 into here, I'm going to get minus 2 in the numerator, and then I'm going to get 3 minus 4 in the denominator. So that's minus 2 over minus 1. So the gradient is positive 2. Okay, fantastic. I'm not interested in the gradient necessarily because I want the normal. Now you remember from year 12 that the gradient of the normal is the negative reciprocal of the gradient of the tangent, and this will be the gradient of the tangent. So the gradient of the normal must be negative 1/2. Okay, it's the negative reciprocal of 2. Now I know it goes to the point 3, 0. So therefore the equation of the normal is going to be y minus y1, but y1 was 0. That's going to equal m, which we know is minus 1/2. And that's going to be x minus x0, which was 3. So that gives us the equation of the normal as being y equals 3/2 minus x on 2. Okay, so that's the equation of the normal. Okay, now to find where that intersects the curve again, I need to solve this in conjunction with the actual curve. Okay, if ever you're looking for the intersect of curves, you need to solve equations simultaneously. So I've got the equation of the curve up here, defined by these two equations, and then I've got the equation of another line here, and so to find where this intersects that, I need to solve this simultaneously with that. So I've got three equations with three unknowns. I've got x and t in here, y and t in here, and x and y in here. So I just need to eliminate all of my unknowns to find values of t, and then hence values of x and y. So what I'm going to do is I'm going to take this normal, and I'm going to use the definitions of x and y from up here. So y was t squared minus 1, and that's going to equal 3/2 minus x, but x was t cubed minus 4t, and that's going to be divided by 2. Okay, so all I've done is I've replaced the definition of y with the function of t, and I've replaced the definition of x with the function of t, and that was from up here, okay, the definition of the curve. This has given me a nice cubic in t, which I can go ahead and solve. So let's just tidy things up to start with. Let's times it all by 2. So I'm going to get 2t squared minus 2 is going to equal 3 minus t cubed minus 4t. And then finally, bring it all across the other side. So I've got t cubed plus 2t squared minus 4t, and then minus 5 equals 0. So that is the cubic. Now we know that this is going to intersect this when t is minus 1, because that is the normal. So I know that t equals minus 1 must be a factor of this cubic. Must be a root of this cubic, which means t plus 1 must be a factor, and then I can divide by it. So t plus 1, that must be t squared, that must be minus 5, that gives me minus 5t, but I want minus 4t, so that must be minus t, to give me the minus 4t. Check the quadratic term, minus t squared, plus t squared. Oh, hold on. Oh, no, I need to go from minus 5t to minus 4t, so I can add a t. There we go. Check the quadratic, t squared plus t squared. There we go, that's 2t squared. Okay. And if you want to use polynomial long division, that's not a problem. But I just did that by inspection. So this has solutions when t equals minus 1, but we're not interested in that, because that is not the point I'm interested in. So I need to solve this quadratic, and that's going to give me t is equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. So we end up with minus 1 plus or minus the square root of 21 over 2. Okay, let's just check which of those is right, because the normal definitely only intersects the curve at one point. So let's try and see what's going on here. So minus 1 plus the square root of 21 over 2, that's about 1.7. That's okay, that's in range. We're told that back in the question, t was between minus 2 and 2. So that's valid. Check the negative one. And we get the number minus 2.79. But that is out of range. I don't care about that one because the curve is not defined at that point. So therefore, the normal cannot intersect the curve at that point. So that's the t value I want, which equates to t is minus 1 plus root 21 on 2. So t is minus 1 plus the square root of 21 on 2. Okay, so that's my t value of where my normal intersects the curve again. And now I can plug that back into here and here to find my x coordinates, and my x and y coordinate. So I'm going to plug that as a plus, that's my exact t value, and then use the definition for x at the top here. So that's going to be the answer into the answer squared minus 4, and that's minus 6 plus root 21. My x value, x equals minus 6 plus the square root of 21, and then I can do something similar for my y coordinate, but the y coordinate was just the answer squared minus 1, and that's 9 minus root 21 on 2. So the exact coordinate is root 21 minus 6, 9 minus root 21 on 2. That's the exact coordinate. And of course we can approximate these. So it comes out as to be about minus 1.417, 2.209. Okay, so that's the 3 decimal place of that. Okay, and as we said earlier, that kind of fits with the graph. It's between -1 and -2, so minus 1.4 fits, and it's slightly above 2 in the y, so 2.2 fits. Okay, so that's the correct answer. All right, thank you for watching. I've got one more video on parametric equations to come, which will be on parametric integration.